Okay, good morning everybody. I hope everyone's having a wonderful day. So before we get started, I just want to remind you that assignment 3's deadline is creeping up. So on paper it is due by the end of June 15th, but as noted, the submission, so the cutoff point for submissions will be sometime, it'll be on the 16th. I made it a little bit later than 8:30 in the morning as noted. So if you just want to double check that, you can just look at the time on the course website. I already mentioned this in a previous message before. So on paper, it's June 15th, but keep in mind, the submission will remain open. You can submit without penalty up until the actual closing time, the cutoff time, which will be, I believe it's early afternoon on the 16th. But yeah, make sure you don't go any time after that. I will not accept it. Anyways, I want to remind you where we were last day. So last day we were talking about there are some issues we ran into when we started talking about our binary search trees, where in the best case, we would end up with a balanced binary search tree where the height is logarithmic. And in the worst case, you end up with a tree that has height that is linear. And one thing that we were thinking about is, okay, so how can we almost place this property that I get something that's kind of like the best case? We're going to sacrifice a constant factor for the height being logarithmic. In our case, last day, we showed that if we impose the height balance property on a binary search tree, that we actually can get that the height is going to be logarithmic. In fact, we proved that it's at most 2 times log base 2 of n plus 2. Which, as I mentioned, it's actually much more rigid than just that. But the analysis we only needed was to prove that the height is big O of log n. So the other piece that we're missing here exactly is how we're going to make sure and maintain, if I start off with an AVL tree, how do I end up with an AVL tree after I mutate or change the tree? So this is where we're going to talk about our rebalancing. So that's going to be the core theme of today, is talking about how we do this rebalancing. So the only time we ever have to rebalance is when we actually change the structure of the tree, namely on put and remove operations. So I only have to talk about those ones. All the algorithms that we've seen for get, put, remove, smallest, all of those algorithms are fine. Just specifically with put and remove, I'm going to have to tack on something else too on those 2 specific operations. So you'll perform these algorithms as we had them before, except we need to tack on some stuff for this rebalancing approach. So what I would like to do is I would like to rebalance the smallest unbalanced subtree. So when I mean unbalanced, I mean that at a given node, it's that it violates the height balance property. Can somebody remind me what the height balance property is? What's the height balance property? So remember, that's the one that dictates that it's an AVL tree, right? So what is it? It's going to play a very important role in today's lecture. So remember, the goal here will be, I start off with an AVL tree, I want to make it still an AVL tree. Well, it's not that the height is logarithmic. No, that's a height balanced BST. I'm asking if what is a binary search tree that we say it has the height balance property. So the height balance property, remember the height balance property. So there's such a thing as a tree being height balanced. And then there's this concept of the binary search tree satisfying what we call the height balance property, which are 2 different things. Just the thing is, when you satisfy the height balance property, you get as a consequence that the height is logarithmic. So that's actually what we proved last day. So remember, the height balance property, that is where if I look at any one of the internal nodes, if I examine the heights of the 2 children, which we defined last time, that each one of the nodes can have a height, which is just the number of nodes it has. Yeah, it's the difference between the left child's height and the right child's height cannot differ by more than 1, right? But this has to be true for every one of the internal nodes. So HL minus HR, the absolute value of this cannot exceed 1. And we proved last day, if you have this property at every one of the internal nodes, you can guarantee the height is big O of log n. So we want to make sure that our AVL tree, when I start off with one, it has this property. And then whenever I make modifications to the tree, I still have this property at every one of the internal nodes. So whenever this happens, where it gets violated, that's what I'm referring to as an unbalancing or imbalance that occurs at a node. So our goal will be, if there's ever one of these imbalances, how to fix it. So we want to make it so it self-balances in the sense that it fixes this so it puts it back into this invariant, the idea that the height balance property is satisfied. So now the whole idea that we're going to use is this idea of rotations. These are very commonly used in different self-balancing trees or self-adjusting trees. This idea of a rotation, you got to think of it just like an operation that's going to happen. I'll do a couple of examples just to give you a flavor for how this works. So what a rotation does, and I'll refer to this usually as a simple rotation or what we call single rotation, but I'll have a specific technical term for a single rotation in a moment. And what it does is it shifts around the heights by rearranging the nodes, but the big kicker, the big thing that we need this operation to do is to preserve the ordering of the nodes. Why? Because we still want to make sure that we have a binary search tree. So suppose that I gave you some subtree rooted at y here, and suppose I wanted to apply this rotate operation. So suppose I apply it to rotate and I apply it on x. So what this is going to do is it's going to promote x over its parent, and it's going to demote its parent. And what this is going to do is it's going to effectively pull up that node that I want to rotate, and it pushes down the parent. And the idea will be is that if we can do this with the appropriate nodes, that we can readjust the heights so that we can maintain this height balance property at an imbalanced node. But remember, it's just an operation at this stage. So right now we're just talking about it as an operation. So if I apply rotate on x, what it's going to do is as follows. It's going to promote x. It promotes x. It gives it a promotion. And it demotes y. And the way this works is it's going to have to, remember, the big thing here is that there's three, so I'm going to have three subtrees that are associated with the nodes that I'm mutating around here, so by adjusting their heights. Some of their heights will change, some will not. So the whole idea here is you can imagine it like I have right now y right here at the top, I have x right here. I'm going to imagine I pull this down like a string. I'm going to pull this down so I can try to alleviate how much heft I might have on one side of this tree and pull it up like a pulley downwards like this. Now, the thing is, I still have to maintain the ordering, so you can almost imagine when I'm trying to make this side a little less tall, what I'm going to do is I'm going to grab one of these subtrees and move it over to the other side, almost like I'm trying to literally balance it, like it's a bunch of weights. So there's this one subtree in the middle that gets exchanged over to the right-hand side. And note that this is a symmetric operation. So you could start off, for example, with this over here, and you can apply rotate to y, and you get what we call, for example, a left rotate. In the picture here, when I did this rotate here, I do a right rotate. So the idea here, very simple, is I promote x, and I demote its parent. Do keep in mind that when you do this, there might be the possibility of an actual parent node just sitting up here. You don't know if you have to check if it exists or not, so you update the appropriate attributes. So notice that there's something very interesting that happens with this rotate operation. So when I give x a promotion, what happens is I promote x and I demote y, but look at the ordering of the nodes when I look at their keys. So suppose that I wanted to do an in-order traversal of this tree, at least this subtree, rooted at y. If I do it in this order, if I just write out what each subtree is, imagining that it satisfies the binary search tree property, watch this. So if I go left, left, okay, I got T1, I visit X, then I have T2, and then I visit Y, and then I have T3 on the right. So this would be what the in-order traversal would look like here. If I do the in-order traversal on the resulting tree, what happens? I get T1 in my in-order traversal, then I get X, then I get T2, then I visit Y, then I have T3. Notice it preserves the ordering of the keys. Does everybody see that? So that means that if ever I use a rotate operation, what we're going to call a rotate operation, whenever I do this, it actually preserves the ordering of the keys. So what can you tell me about if ever I gave you a binary search tree and I applied a rotate operation on it? Would it still be a binary search tree? So if I pick one of the nodes and I try to rotate on it, yeah, it won't change or violate the binary search tree property. It's still going to maintain the ordering of the keys. The only thing that happens is we readjust the positions of the nodes, and as a consequence, we may adjust the actual heights of the nodes themselves. So this is actually going to make it valuable as a mechanism for rebalancing the tree. And many self-balancing trees or self-adjusting trees use an operation defined like this. So, okay, so just remember, whenever I apply to one of our nodes, I'm just going to promote that and I'm going to demote its parent. So notice that I'm defining it in the context that I actually have a parent. If I don't have a parent, no rotation happens or anything. It's just, if I was at the root and I apply rotate, nothing's going to happen because I don't have a parent. I have nothing to promote. So is the idea of the rotate clear, everybody? So that's all this is. Now, you might be staring at this say, Dan, well, what's going on here? Like, so you change the structure of the tree. So what is that like? Can you show us a couple of examples? Yes, and that is the plan. So I want to start off with a very basic tree first. So suppose that I gave you just something like this. Start off with something basic. Suppose I have 1, 2, 3 like this. So keep in mind that the rotate operation is just, like I said, it's just an operation you can apply to the tree. Just like how we talk about arithmetic with numbers, I can talk about a rotate operation on a tree. So given a specific node. So it's something I could do with the tree given some node. So if I were to, for example, try to do rotate on 1, whatever the node would be for 1 here, notice here that, remember, the whole idea is I need to give 1 a promotion. So it means that I need to identify the subtrees that I have here. I have my left subtree of X, I have a right subtree of X, and I have the right subtree of Y. Notice that I identified these because I know I'm on the left of my parent. So I'm going to just identify these 3, and it makes it actually a little easier to see how this works. So I have 3 subtrees, right? T1, T2, T3. This is T1, that's T2, T3. And what I'm going to do now is I'm going to give 1 a promotion, and I'm going to promote it. So 1 gets promoted, and that means that 2 gets demoted. It means we're going to be doing a right rotate. So 2 gets demoted, and it says to put T1 right here on its left still. It doesn't move anywhere. It still has the same height. Then notice that I have T2. T2 is just going to go, it's going to get handed on over. It's going to juggle it over to the right subtree. And then I'm going to have 3, which is T3 here. That's still going to be on the right of Y. In this case, Y was 2. So when I apply this rotate operation, notice by promoting 1 now, I've pushed 2 down. Does everybody see that? So I'm just trying to make it clear that this is just an operation you can apply. So you can imagine it's just a function that you can call on a given node. So is this example clear, everybody? There's There's no spooky magic or anything. All I do is I'm making some pointer adjustments. That's all that's happening. Now, at first you might look at this and say, Dan, well, that's kind of cute, right? But like, how does this help us rebalance the tree? So I thought I would do one more example just to illustrate my point. So let's do one more example here. I might have to draw it here, then drew the result on the right side here. So just keep in mind this picture when we're doing this. So remember, it is symmetric. So this is a reversible operation. So if you just did rotate X here, you'll get that over there. If you go rotate Y, you'll get back that over there. So let's do another example. Suppose I give you 2 where its children are 1 and 4. Then the children of 4 are 3 and 5. And then I'm going to have one child for 5. It's just going to be a 6. Let me just get out of the way here for you. So remember, in our AVL tree, we're actually going to be storing all of the heights. So if you look at this carefully, all the leaf nodes, remember their height are 0. Then 6's height is 1, 5's height is 2, 4's height is 3, and 2's height is 4. I have a question. Now keep in mind, you could do this for all the nodes. For example, like all of our leaf nodes have height 0, 3 has height 1, and 1 has height 1 as well. So, question. Is the example I have on the left board an AVL tree? It's not, right? It's not. Can somebody tell me why? Why is it not? At what node, which internal node am I getting an imbalance at? Which internal node am I getting an imbalance at when I compare the left and the right? Which one? It's 2, right? Right here. Notice it's 1 versus 3. That's greater than 1. So the difference is more than 1. Exactly. Exactly, everybody. So I'm going to show you how you can use the rotate operation to correct this. So watch this. So you notice that I have an imbalance here, right? Well, look at this. So this is the node that I got the imbalance at. What I can do is if I identify the correct node to perform this rotate operation, just like when I talked about having my pulley here, you can see clearly that the right side of this tree, the right side is it's taller than the left side. You can imagine like it's heavier. So what I'm going to do is I'm going to drag its parent onto the left subtree and promote the child that's on the right subtree up to try to alleviate this, to try to balance it out so that we can still maintain the height balance property. So you just imagine it like I'm pulling a string and I'm just trying to pull that up. Now remember, I still exchange over another subtree in the middle. So unless I absolutely am certain I have like the true smallest possible imbalance that it can happen. Say if I started this process, say at a leaf, for example, or the smallest, the leaf node, sorry, an internal node just beside leaf nodes at the furthest depth in the tree. If this happened, or at the furthest depth I can go for a certain branch, I can ensure every time I'm examining a smallest possible AVL tree that potentially got violated, and now it is imbalanced. But sometimes this isn't true, and that interchanging middle subtree can be a bit of a problem when it comes to that. Here, it's not going to be so much of an issue here. So I'm just bringing that up because it'll matter a little later. So anyways, if I look at this, based on what I just suggested, suppose that I try rotate on 4. So if I go rotate, on 4, notice that by my idea here, I'm going to give a 4 a promotion. I'm going to bring 4 up and I'm going to demote my parent. That means that the height, this height here, so notice that the height here is 3. If I bring this up, that means that I'm going to actually increase the height of the left subtree when I promote this this one here up here. Notice that this subtree will no longer, this node's height will no longer be 4, it will be instead 2. So if you actually compare it now, it'll be something a little bit more reasonable for our height balance property, right? So I'm gonna show you what the result of this will be over here because I'm sort of running out of space and I wanna make sure we keep this picture here. So if you're ever just really not sure what to identify, because this tree is a little bit more complex, I'm just gonna identify the 3 subtrees. So I have T1, T2, T3. So I wanna rotate on 4. So notice that I have, now remember, here it will actually be, is this a right rotate or a left rotate? It's a left rotate this time. So now you got to look at this picture. So the way I know it's a left rotate is because if you look at the parent, I'm on the right of the parent. So that means I'm going to have the 3 subtrees. I'm going to have one right here. There's one right there. I got another one right here. And then I have this one right here. Then, now let's do the eureka moment. So I'm going to promote 4. 4 is now the root of this tree. I'm going to demote 2. And now notice that T1 has to be on the left still of 2. So it means I'm going to have 1 right here. And I'm going to have to juggle over the middle subtree, right? The one with 3 right there. So it means 3 is going to go right here. So it just hops on over. I trade it over. And then I just put the right subtree in. So the right subtree I have, so I have 5. And I have no child for the left, except it's just a leaf node, right? Then I have 6. But now look at this, look at this. If I look at the heights, 0, 1, 2, and the height of 4 is 3, like before, right? But now notice that the height of 3 right here specifically didn't change, right? Because all I did was I just demoted its parent. It doesn't matter because I'm still a subtree with my own height. It didn't affect me. It's almost like the whole world is moving around me, but I didn't change at all with respect to the rest of it. Except I'm just in my own little planet here, just kind of hanging out. So I got a 1 here. But now notice that the height went down as I said. It went down. But now, do we have any imbalance anymore at, say in this case, 4? Is there any imbalance anymore? No, right? So you're going to see that this rotation operation tends to be pretty useful, right? Just like I said, if one side gets too heavy or too tall, we can use the rotation to readjust the heights so that we can try to rebalance it. So that's the place where rotation is going to fit in all of this. So are there any questions about the rotate operation? And I must stress that normally when you implement this operation, you don't have to distinguish between left rotate and right rotate. You can just implement this as one function and it just has these two. You just have to identify if it's a left one or a right one. And notice very clearly that all that's happening is I'm just adjusting pointers, right? There's nothing else going on. Adjusting pointers. Actually, there's one other detail that we also need to update. What is the other thing I need to update? There's something that I left out here. But I implicitly did it, right? There's something at the nodes I have to update too. The height, yeah, exactly. So the parent, oh yeah, the parent too, because like I said, it kind of falls into the pointer adjustments, but most certainly the heights. Whereas remember, we're maintaining, like we talked about last day, we're maintaining the heights at the nodes. So this is actually an attribute we're going to update. And I gave you a very, very, very short algorithm that just recomputes the height. So notice that if I just ensure that I actually have an internal node there, I could just update the heights of the nodes that are affected here. But here's the catch. Here's the fun catch of this whole thing. What's the time complexity of performing a rotate operation? Any ideas? Remember, I didn't write down pseudocode or anything for you, but you can see that this is all that's happening, right? I update the heights at nodes that are affected. Note that, like I said, it is symmetric like this, so you can easily just adjust it so that you would only, like whenever you know it's a right rotate, you update certain nodes. When it's a left rotate, you update certain nodes that are affected. And keep in mind, you can also be generous with the way you update the nodes, right? You know that there's like, okay, there's this node that maybe get affected. This one might get affected depending on which case I'm in. And also, I notice other than that, these subtrees are just getting wiggled around, right? So far I got one suggestion for constant time, and that's in fact the case. So the time complexity of performing a rotate operation is constant time, because all it is pointer adjustments, then I call update the heights on the appropriate nodes. That's all that's happening. So that is another perk of the rotate operation. It takes constant time. So it means that if I'm ever need to adjust at a given node, I can just do this in constant time. And the idea is that I would like to make sure that when I perform these rotate operations, I don't do too many of them. So is that clear, everybody, why this takes constant time? It's just pointer adjustments and updating the heights at a few nodes, tops. Usually you can get away with updating a couple if you're very careful about it. In fact, some of the algorithms I'm going to give you actually automatically update certain nodes so that you can kind of thread them together nicely. But either way, you can get away with updating the heights at nodes. And like as long as some constant number of them, like 2 or 3 of them, it doesn't make any difference. Isn't that cool? So we have this rotate operation we can do. And the reason why I introduced you this first before we get into any of the details is because, like I said, this concept of performing a rotation is used in a bunch of different self-balancing and self-adjusting trees. So some people define the rotation operation at a given node, then they define left and right. Others will be like here, where we have it where it's just oblivious and automatically performs a left or right rotate based on its orientation with respect to its parent, which is the way we're going to do it here. So is this sounding pretty cool? So give me 2 thumbs up if we're good to go. So if you understand this rotation, you understand actually the biggest part of this process. So if you understand this, you actually have the key ingredient to understand everything I'm going to tell you in this lecture. So let's see how we're going to use these, okay? So you just think of it like an operation I can use. So the way the AVL tree is going to get rebalanced, assuming I'm at the smallest or the first encountered imbalanced node, I'm going to apply different kinds of rotations. There's 2 main families of rotations. In total, there's 4 kinds because there's 2 kinds, each one symmetric with each other. So that means there's 4 in total. So there's 2 kinds. There's what we call single rotations. So single rotations. And the other is called the double rotations. So there's 2 of each kind. So I'm going to first start off with the single rotation. So all it is that you're going to do a single, or what we call the simple rotation over here, a single left or right rotate from the tallest child of an imbalanced node. And suppose that imbalanced node is Z here. So suppose that you have the situation very much like my example I had over here. In fact, this should remind you a lot of that example because it's the exact same case. So notice here that if I have an imbalance that happens at node Z, and suppose I look at my 2 children, and I say, okay, well, which of my 2 children has a larger height? That is what I mean by tallest child. So if there's ever a tie, usually the rule of thumb is that you always go with the same side for which your parent would be on if there's ever a tie. So I'll get into more detail about this in a moment. So the point is if this side is taller than that side for its 2 children, then we identify this as Y, which that is the taller of the 2 children of the imbalanced nodes. And then I determine the taller of its children, Y's children. and I figure out which of those is taller. And whichever child is taller, meaning it has a larger height, I call it X. We're going to see that identifying these three nodes, this tri-node structure, as long as you identify these three nodes, we can figure out what kind of rotation we need to do. So these all have different names, by the way. So, for example, if I know that the taller of my two children is in fact on the right, and I know that my taller of the two children is indeed also on the right, we're going to apply something called a RR rotation. It is a kind of single rotation. And all it is we apply rotate on the child that is the taller of the two of the imbalanced node Z. So if ever there's an imbalance where we get the violation of the the height balance property, you just pick the taller of the two children, you apply rotate on that node. And that's what Y is. So if you walk through the exercise akin to what we just actually did over there, what happens is we promote Y and we demote Z. And what this will do is it'll do something just like we did over there. Where what's going to happen is it's going to adjust the heights. And you'll notice that based even on my picture here, I don't claim that this is a very accurate picture other than the orientation and position of the nodes. You'll see that if you look at this tree versus that tree, this tree looks more balanced than that one, right? But it's the exact same principle we just went through with this example here. So by pulling up the taller of the two, I'm just pushing down Z. And by doing that, I'm actually giving a little bit more heft or weight over to this other subtree over here, making it slightly taller. And by doing that, remember, height of Y doesn't really, it might change if there's ever a subtree that gets just exchanged over, but most certainly in this case, the idea is I'm trying to cleave off Z, so I bring it down, so it becomes that it's more balanced. So this is what an RR rotation is. An LL rotation is a symmetric case of this. So instead, Z has it where the taller of the two children is on the left. And same idea as before, we call this an LL rotation. You might ask, why is it called RR rotation? Why is it called LL rotation? You'll see exactly why in a moment, but I'll give you a bit of a hint. Notice that when I examine the taller of the two children, it's always on the right here and always on the right here. And whenever it's on an LL rotation, I do it on the left. And notice that the taller of the two children is always on the left when I determine these two nodes. And the same idea here applies. So this is all I have to say about single rotations. A question. What's the time complexity performing a single rotation? And yes, I am deliberately covering this side of the board. It's constant time, right? Because all it is just one rotation. That's it. And we know that performing the rotate operation takes constant time. So this is one of the ingredients. And you're going to notice that by laying it out like this, we've covered two possibilities out of possible 4 cases that can happen. So if I'm looking at the two possible children, so the child and grandchild of an imbalanced node, notice that there's 4 possibilities that can happen, where it's to the right, to the right, to the left, to the left. What are the other 2 possibilities going to look like then? So there's 4 possibilities, hence why I say there's 4 in total. What are the other 2 going to look like then? So what are the other 2 going to look like then, if they're thinking about all possible ways that the node can get imbalanced? So it could be that the taller of the 2 children's on the right, and then its child is on the right as well. Yeah, exactly. Somebody's suggesting left, right, then right, left. Yes, exactly. Those are the last 2 cases. These are going to encapsulate the idea of the double rotation, which, as you might see in a moment, notice that when they're straight like this, we don't have to do a whole lot of stuff, right? I can just take the same idea we just talked about, how we can fix up that imbalance by just simply tugging on it. But there's sort of a problem when we have it where it kind of goes right then left, or left then right. We have this zigzag-like pattern. Notice that it isn't straight like this, like in my idea where I pull it by a pulley like this, where I pull it and I try to balance it out like this, we're gonna have to knock out a kink out of it. We're almost like a kinked hose when you're trying to spray some water. We're gonna have to fix that. So let's talk about the double rotation then. So these are actually just the last two kinds of rotations. And remember, at the heart of them is just applying a rotate operation. That's all it is. It's just you have to identify the correct nodes and how many times you need to do it. So you might ask, Dan, what makes the double rotation so dang special? So let's talk about that. So we have the double rotation. Like I say, usually people come up with these terms for very logical reasons. So we had the idea of a single rotation. It just uses one rotate operation. What do you think is going to happen with a double rotation then? Any ideas? What's going to happen? Well, if it's called a single rotation over there, then surely a double rotation is going to do two rotations. So this is going to happen when the tallest descendants of an imbalanced node form what we're going to call colloquially, this is actually technically a technical, well, I'm getting very excited here. If they form what we call a zigzag pattern. So this is actually a technical term. Now to fix this, we're going to use what we call RL rotations and LR rotations. So let's see what this is going to look like. So you're going to see, I'm going to draw a picture that's very similar to the one that we had just on the board over there. It's just going to encapsulate the other cases. So I have the three nodes, right? The imbalanced node Z. We have the taller of the two children, Y, and then we have the tallest grandchild of Z, which would be X. Suppose I have T0, and then we have T1. Actually, yeah, let's do it this way. T2, and then we'd say we have T3 like this. Okay. You're going to see that the structure of this is a little different than the ones we had over there. And our whole idea about like the pulley idea. Now, naturally, when you're like, imagine this like I'm trying to straighten out my string so I could keep pulling the pulley so that I could try to balance it. What I want to do is I want to straighten this out. I want to straighten this out so that I could continue to pull. So I'm going to show you the RL rotation here. So the way I could do this is, notice if I want to make it nice and straight, kind of like that kind of rotation I had over there. Well, think of it. Think of this. If I do a rotate operation on X, so notice if I take X and I give it a promotion and I demote Y, notice that then they'll put it so that it's Z, X, then Y, right? Because Y will get demoted, then X will be the new parent among, well, Y used to be the parent, right? Now that will be X. So notice that that's now nice and straight, but notice what position X is in now. So if I'm doing a double rotation, and now it looks something much more like the other case over there, which node should I apply rotate to then? So I want you to think back to this picture I had over here. Just keep in mind, so let me just kind of go over here just slightly. So remember, when I promote X, what's going to happen is Y is going to go down and X is going to go basically into its spot. So which node should I apply rotate to then as a result? And I must stress it won't be necessarily the same node as I had in my RR rotation. Which one will it be? So I got two suggestions. I got Z and I got X. So if we try doing it at Z, now remember, when we did this process before, because remember, Z might possibly be the root of the entire tree. So I may not do anything if that's the case. Another thing is that the imbalance is happening at Z. I would like to correct it by trying to adjust the heights of its two children. So maybe Z isn't the greatest of choices, possibly. Maybe in some cases it might be. Yeah, no, so somebody is suggesting X. So if you did a rotate operation on this right here, if I did rotate X here, remember, I'm going to pull X up, I'm going to give it a promotion, Y comes down, and then if I did so notice that X will be in where Y's position is over there. Now keep in mind that they may not necessarily have the exact same kind of heights that we would expect over here, but it most certainly will have the same layout, except they'll be Z, X, Y. So if we do rotate on X, it'll indeed, as suggested in the chat, somebody suggesting that in this specific tree, the one I just drew here, it would become the new root of this subtree, rooted at Z. Now Z will become demoted, then X becomes the new root of the subtree. So as a result of this, what happens is I end up with something that looks like this. So I end up with X right here. Z gets demoted, right? And because Y was demoted before, it's going to end up being the right subtree for X. So the node that we focus on in the double rotation is X. So every time you do this, normally the way it works is that when you do your rotate operation, you return whatever the root of that subtree would be. So when I do rotate X, the resulting root of that subtree would be X. So are there any questions about this double rotation here? So the whole idea is I'm trying to like unkink it because it's sort of stuck. So I'm going to use one rotation to readjust that. So one thing I want to point out is that the LR rotation is just symmetric to this one. But I'll include it in the notes as a picture. But the LR rotation. So it's just symmetric to this. You still do I was about to say rotate. That's when you know it's a Wednesday. Rotate X twice. So these are actually all 4 kinds of rotations. So if you just remember these 4 rotations, you're good to go. But really the greatest part about this is that as long as you remember the structure of these 3 nodes and you know what a single rotation is versus a double rotation, that's even better. Because then you'll know, okay, well, I just do 2 rotations here on one node, so you just have to remember which one. And in the single rotation, you do it on Y. So you might ask, Dan, you showed us all these rotations, so how are we going to use them? Like Dan, like how do I know I'm going to get this node Z here? Like how do I know which rotation to apply? So I need to address this. So let's talk a little bit about this. Wait, I got an eraser over there. No, I must beat the camera. You guys are catching up to me. Okay. Oh, you guys are gonna win. Oh, man. Or am I? Oh, this is gonna be close. Ha! No, 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 no! Oh, man. I lost. The camera beat me here, okay? You guys caught up to me before I finished erasing. So, the question is, how do you determine which rotation to apply? So that's a big question. Going to serve as the backbone for how we're going to do this process. So surprisingly, it's really simple. So it's surprisingly simple. So all you do is determine the tallest child, y, of the imbalanced node z, then determine the tallest child, x of y. So that means that all you do is you read off whether y is on the left or y is on the right, and if x is on the left or x is on the right. So you read z, y, x. Is y left or right? And is x left or right? Let me just switch this marker. This one's getting a little funky on me. It's gone now. It's gone now. So for example, if I was reading off z, y, and x and I find out if it's on the left or on the right, I just read it in order starting from z. So if I find out that let's say z is on the, z's tallest child is on the right, I figure out that is that's y, right? And then I figure out, for example, that x is on the left of y. What kind of rotation would I apply there? So it's saying I'm going to the right to get to y, then I go left to go to x. So I would just apply the RL rotation if that happens. So very often the way you would just simply check this is you would check, once you determine the taller of your two children from the given node that you're looking at, in this case you start off with z and then you check y. What you would do is you would just figure out if your node's left child or right child is that node. If it is, then you can figure out if it's on the left or on the right. So you ever wonder, like, okay, so what do we do if we ever have a tie? If ever a tie, go with the same side. So keep in mind that the ties at y, it must be that they don't match. Because by definition, the height balance property was violated, right? If there's ever a tie, it'll happen at x. So like when I determine x, if ever I have it where I could pick one of two nodes to be X and there's a tie, you always go, it's usually recommended in practice that you always go with the one on the same side as whatever Y is. So you might ask, okay, so why would that be the case? So if there's ever a tie, and say for example, I determine that Y is on the right of Z, and I end up there's a tie for X, it can be either the left one or the right one. If I pick the right one, notice that I get an RR rotation as opposed to an RL rotation. Why might I want to do that as opposed to the double rotation? So if I did RR instead of RL, is there any suggestions of why I would pick the same side as whatever side that the original taller of the two children was on? Any suggestions at all? So think about it more. It's not necessarily from a complexity standpoint. Think more about this from a performance standpoint. So think of it in terms of, okay, yes, doing 2 rotations, for example, that's still constant time, right? But think about it. Think about it. Would you rather want to have to do 2 rotate operations or just 1? You just want to do the 1, right? So this is actually why this is often suggested. Now, it doesn't make any difference. You just want to just do 1. It's much better. So if you're doing many, many rotations, as opposed to doing 2 of them, you could just do 1 of them. So that's why I suggest this. So it doesn't change the time complexity of these algorithms at all. It's something that if you try doing this, you'll find that the outcome performance-wise will be better because you don't have to do as many rotate operations. So that's all I have to say about how you determine which rotation to apply. So if you find out you're an imbalanced node, all you have to do is determine these 3 nodes, and you just read them off like that, and you figure out if it's on the left or on the right. And that's it. So one other thing I did not mention is about this height business a little bit. I mentioned about it, but I didn't say something a little bit more about that. So one thing I also need to mention is that the order you recompute heights matters. So for example, if you're doing an RR rotation, what you'd want to do is you would want to update, if you need to, you would update if necessary. Like keep in mind there might be a leaf node there for some reason, but if you don't have that, you have an internal node, you can update the heights of, because remember in an RR rotation we promote Y, right? So it means that we have Z on one side and we have X on the other side. So we update the heights of Z and X first, then Y. If you do it in the wrong order, the height calculation will actually be incorrect sometimes. So just be very mindful of the fact that this happens, but also remember in a double rotation, since it applies the rotate operation twice, keep in mind that you'll have to update the heights appropriately each time you do one of these rotate operations. So you can imagine it like literally you're just implementing this whole operation at once, which you can implement it like that. You can literally just do all the pointer adjustments so you make the one picture on the left look like the right one. You can literally do that. Or you can think about it in terms of the rotate operation, for example. Either way, you have to make sure you update the nodes in the appropriate order. Otherwise, you're going to recompute the height on the wrong node, and you're going to end up with the wrong outcome for the height. Meaning that you'll see this strange behavior where the height will suddenly jump up or down in a way that doesn't make any sense. Or it even may stay the same when it's not really supposed to stay the same. So are there any questions so far? So I've laid out all of the key ingredients for us to start talking about how we're going to do this rebalancing process. So I gave you all the mechanics for how we're going to do this. Just now the question is how we actually do this rebalancing process. So how do we find the smallest imbalanced node, for example? We haven't talked about that yet. We just sort of presumed we could find it. Sometimes we might not be able to find it. In some cases, we might have it where it might be the first time we encounter it, but it may not actually be like at the closest or at a leaf node that's towards the bottom of the tree where I examine and go up or something like that. It might be somewhere else on the tree. So, if we're okay with this, are we doing okay so far? Any questions at all? Okay. So if we're okay with this, let's start talking about how we're going to put all of this in together. So we're going to put all the pieces together now. So depending on how far along we're going to get, we might not do removals today. We'll probably do it next day. We'll probably just focus on insertion and how we do this rebalancing process today. Because once you get the idea, the removal is not too much different. There's just one little caveat that I've been sort of planting the seed of for a little while now. So let's talk about how we would do the insertions first. So I'm going to describe something we're going to call putAVL. And naturally, it is going to be the insertion for an AVL tree, hence its name. So all we're going to do is we're just going to first apply put, as in a binary search tree. And then we rebalance if needed. So one thing I want to mention to you is, actually, it really comes up to this. So remember, when we do our insertion, we do it always at a leaf node, right? We always go to a leaf node, correct? So keep in mind that if we go, we're going our way down to some leaf node. When we go there, what we're going to see is that we can actually start at that node for which we did the insertion. And we can work our way up the tree, seeing if we can find this imbalanced node by following the parent. So we just follow the parent pointer every time you can go up the tree. And the goal will be just to simply check if the height balance property is being satisfied. Did an imbalance happen? But here's the fun catch you get with the insertion. Because we always start at a leaf node, and every time we're progressively making larger and larger subsets of an AVL tree, or what we call larger and larger subtrees of the AVL tree, every time we're considering larger and larger and larger, but we're always starting at a smallest one, we always know, as I start off at that leaf node and I work my way up, every time I do this, I know the heights are only going to get bigger. It's not that I'm going to have one kind of sitting off here that's going to be way bigger possibly, and I haven't examined both sides of it or something like that. So this is a neat catch that you get for the insertion, is that we're going to have at most one rebalancing operation that's going to happen. So at most one's going to happen, but the algorithm I'm going to present to you will be oblivious to this fact. It'll just do only one It's going to apply one of the 4 rotations, but it's only going to apply at most one. So this is one thing that's nice about insertion. So what I'm going to do is I'm going to first start off by giving you putAVL. The pseudocode for it, you're going to see I'm going to push a lot of the complexity of it to this other function I'm going to call rebalanceAVL, which is going to do the rebalancing operations. So let's first write out putAVL. So we got putAVL. It's going to take in some node, root node R. It's going to take in some record data. So a record. So as input, we take in a root R of an AVL tree. And we have record, and we're going to get a record K data pair. Then next, So this one, I'm just going to make it so it just does the insertion, but you can easily modify it to do all sorts of different things. So insert the record K data and rebalance if needed. So for example, you can easily modify this if you need, for example, this to do more for you. For example, to report the error if you get a duplicate key. I'm not going to focus specifically on that here. It's very easy to... We've already talked about this before. So I'm going to just start off by applying put. So this is the put that we had from the other day. And like I said, I'm just going to So I'm just going to presume that there's no duplicate keys when I do this. If not, you can easily add an if statement, just checking if the insertion was successful or not. Just immediately after this, you can make that return a Boolean value, for example, if you wanted to. Or you could just simply make it so it throws the error inside of this function. But what I want to have is I'm going to have this give me a node, let v be the node where the record K data was inserted. So if ever it becomes unclear and you have a difficulty trying to get this node, you can always use the get operation to retrieve it. So if you don't make that return this node, you can always make it so it actually uses the get operation to retrieve this node for you. And then lastly, it's going to just call a function we're going to call rebalanceAVL. And just remember, at most one rebalancing operation is going to happen here. One of those types of rotations is going to happen. So let's just quickly go through the analysis here. So I haven't talked about that algorithm yet. We're going to talk about that in a moment. But notice everything here that I've just described here, you can do all of this in big O of H. So this first two lines I could do in big O of H, right? Where H is the height. So the real question is, what's going on with rebalanceAVL? Let's take a look at that. So now I'm going to go into rebalanceAVL. And I want to stress our algorithm is going to be designed so that we can use it both for the insertions and the removals. So you're going to see that this function is going to play a very key role in how we do this rebalancing regardless. And it essentially matches what I've been giving you the idea about, that you kind of start at some node and you work your way up. And whenever you run into an imbalanced node, you're going to apply the rotation that you're going to need to do, which we talked about which one you would pick. So here we go. So we got the algorithm called rebalanceAVL. And it's just going to take in, for us, it's just going to take in this node V. The first thing I really want you to be aware of is that this node V is going to be like, it's going to play the role of Z that we talked about earlier, the one that becomes imbalanced. If ever it becomes imbalanced, this node will be V. If that occurs, of course. So input, it's just going to be node V, where imbalance may happen. And it's not going to return anything. It's just going to update the AVL tree. To be balanced. So that we can maintain its height as we talked about as a logarithmic height. So here we go. So first I'm going to start off by checking if V is not a leaf. If V is not a leaf, then if it is not a leaf, then you want to recompute its height. You know how I talked about yesterday, how I talked about, oh, at some point this algorithm is going to recompute the height of an internal node, so it sets it to be 1. That's this right here. Because you got to imagine this being called on putAVL. So if it's not a leaf, they're just going to recompute the height at that node. And remember, if I do an insertion, I'm at that node right now. I'm at that internal node. So that internal node, when I call this, will update its height to be 1. So that's what I was talking about last time. Now we're going to have a while loop. Now while v is not the root, so while v is not the root, we're going to do the following. So we're going to do the following. So I'm going to assign v to be the parent of v. So I'm going to work my way up the tree. Every time I'm going to examine that node to see if it violates the height balance property. So if the subtree rooted at v is not AVL, then, so just remember, what this is saying is it's checking that the absolute value of the heights of its children, it's asking if it's greater than 1 when I take the absolute value of the difference like that. That's what this is checking. So you get the heights of your left and your right, and you check if they differ by more than 1. If they do differ by more than 1, then we have to do our rotations, right? So, just like we talked about, now I need to figure out what kind of rotation I need to do. So let y be the tallest child of v, and let x be the tallest child of y. So just to remind you, v is z in our discussion at this point. So just a reminder, remember if there's ever a tie, you just pick it onto the same side, as we talked about earlier. So I'm just going to mention that as a comment. If ever a tie for x, pick on same side as y. Just gonna fix that E. That E looked a little melted in there. Now, since we know our V, Y, and X, those are the 3 nodes. Remember, V is Z. So now all I'm gonna do is apply the appropriate rotation. So I'm gonna rebalance. So now that I have that done, then I'm going to rebalance subtree rooted at V with appropriate rotation. With the appropriate rotation. And of course, when you're doing this, make sure you update the appropriate heights. And then, after you're done this step, you're going to let V be the root. Let V be the root of the resulting subtree. As I suggested earlier, if you make your rotate operation actually return the node of that is the root of the subtree, you have access to that directly. So that ends the if statement. So this will do the correction. Then, once I've done this, I'm going to recompute the height at that given node. You might ask, Dan, why does it recompute the height as it goes up? Well, think of it this way. I still need the mechanism to update the heights whenever I do an insertion, even if an imbalance doesn't happen, right? So for example, when I work my way down the tree and I put a new record in, I'm going to create 2 leaf nodes, and that's now that node that I put it in, now it's going to have height 1, and I'm going to work my way back up the tree, and I have to increment the heights of each one of the nodes as I go back up to the root, right? This is what this line is for. And that wraps up the while loop. And that's it. So you might ask, okay, so what's the time complexity of this right here? Well, let's think about it. Inside of this loop, inside the loop, okay, getting the parent, checking this, that's just an arithmetic calculation. This we know how to do in constant time. We know how to do the rotation, whichever one it is in constant time. We know how to get this in constant time. We know how to do all of this in constant time. All of this inside the while loop can be done in some constant C2 many operations. The if statement, checking this, I could do that in some constant C1 many operations. And remember, there's a possibility that I could start actually at the deepest node, or what would have used to have been the deepest node in the tree. So how many iterations for this while loop can happen? So how many complete iterations can happen? What would it be related to? Well, I haven't gotten to the logarithm part yet. I just want to put this together. So I have C2 times the height, right? So if I put this all together now, we can see the following, right? We know as h is big O of log n, the worst case time complexity is big O of log n, right? So that's for rebalance AVL actually takes big O of log n time. Big O of log n. That says log n there. It sort of just melted into the side of the board. So that brings us back to our insertion. So let me just put this all together. So last bit of our analysis, then we're going to stop here. So now I know something great. We know that the time complexity is big O of h for rebalance AVL. So we've determined this is also big O of h. But because like last day we actually proved that h is big O of log n. As h is big O of log n, putAVL takes big O of log n time. So now we can successfully do insertions in logarithmic time. And now keep in mind, all that's left now is talking about the removals, and then we actually have ourselves a data structure that's capable of doing these logarithmic operations. So anyways, we're going to stop right here. When we come back, I'll do an example of us doing the putAVL with an AVL tree so we can see how this actually plays out step by step. And then we will go to how do we do the removal, and then we'll see some properties that AVL trees have, and we'll see where we go from there, okay, everybody? So I say thank you very much, and have yourself a beautiful day. I will see you tomorrow.